what is this virtual earth method? So this is again proven a very effective method to solve a group of static problems, particularly the problems of equilibrium involved with connected bodies. Correct? So this method is suitable for problems involved with the connected bodies. So the connected bodies can be connection by pin joints or connection by mere contacts and so on, right? You also know different types of constraints, different types of supports, right? So basically it is an alternative method to solve such kind of group of problem when those connected bodies are acted upon by external forces and the body remains in static equilibrium, right? That means what? The body has to be appropriately constrained. The constraints are the constraint forces from the supports, and those forces along with the external forces ensures the static equilibrium. If that is so, what do you mean by this virtual earth method? How do you define this virtual earth method? So let us define the principle of virtual earth method as this. So it states, this method states that if a particle or a rigid body, this particle word you should not misunderstand, as I was telling from the very beginning, very first class. A particle refer to a rigid body when the physical geometry of the body is not considered, right? That's why it is said if a particle or a rigid body or more generally a system or more generally a system of connected bodies a frame structure formed by multi-force members as well as axial members is an example of connected bodies. A truss system where there are many members which are connected in a particular fashion in order to bring out a structure called truss, transfer the loads. These are all examples of connected bodies which is in equilibrium. So this is an equilibrium if we consider in equilibrium, which is an equilibrium under various external loads, under various external forces when they are acted upon like that, what is that you are going to consider is instead of the system is going to resist supported, when you look at a free body diagram, the system of forces. So you will give a displacement consistent to the constraints, right? Forces is given an arbitrary displacement from the position of equilibrium, from the position of equilibrium. The total work done by the external forces during the displacement is zero. Is zero. So this is what is called the principle of virtual work. What is this called? Principle of virtual work. Let me once again read out what I have written on this. A principle of virtual work states that if a particle or rigid body, or more generally a system of connected bodies which are in equilibrium under the various external forces, is given an arbitrary displacement from that position of the equilibrium, the total work done by the external forces during the displacement is zero, is what is called principle of virtual work. So you understand here, see, if you may say that where is the displacement comes into picture. If you say a system of forces acting on a body and body remains in static equilibrium, there is no displacement, there is no deformation of the body. The state of rest condition is ensured. That's what is called static equilibrium condition. But when you say that there is a displacement, and those displacements are called virtual displacements. That is why the method is called virtual work. So you assume that though there are constraints, the body and the static equilibrium, you know that in hand. But if we consider the external forces are going to produce an arbitrary displacement from the equilibrium position, and then you are expected to calculate the total work done of the system. Because if we have a force acting on a body and there is a displacement due to that, and you would be able to define work done by that force on the body. So there is work done in the system. So when you know that there cannot be no displacement, but you assume that the displacements of taking place from the equilibrium position consistent with the constraints offered in the system of connected bodies for an external forces, the sum of the total work done is said to be zero, is called the principle of virtual work. So the displacement is called virtual displacement, and the work done is called virtual work done. So when you say this virtual work done is zero, that means the displacements are not taking place. But the reality is the forces, external forces, are the system forces in a body. That is in real. But the displacement is virtual. So when you get the virtual work, and that has to be zero, is what you say, is what is principle of virtual work. So the total work done from one position to the other position is what is equal to zero. When you say in a system, then it is called virtual work principle, right? So how do you go and solve this problem? So for that, let's look at beforehand what are all the important definitions. So you know how do you define work of a force? Let's see one by one, and let us understand what all the forces would create work, what are the forces will not participate in work done equation, right? So let us look at, it's not so big, work of a force. Why do I write work of a force and its definition? So that you would also understand what do you mean by work of a moment or a couple, right? So work of a force, the du, I can define as F vector dot dr vector. So what does this dot product refer to? F into ds into cos alpha. If I define the system is like that. So I have a point A refer to a particle, and this point is acted upon by a force, say F. And this force is making this to go to a next instant distance. Then this position vector, the displacement is dr. If you see this force vector and the displacement of this point to A dash new position is given by dr, then the work elemental work is F dot dr, which is F into ds, so ds into cos alpha. So if you see here, I can represent this with respect to a reference point O, where position of A is given by r vector, and this position changes to A dash by r plus dr vector. Then the change in position is given by dr due to the action of this force vector on the particle A. And where the angle included by these two is given by angle alpha, then I can define my work done due to this finite displacement dr is F dot dr. It is defined as F ds cos alpha. So positive work if means this angle should be an acute angle. If this angle alpha is less than 90 degrees, 0 to 90 degrees, between 0 to 90 degrees, then it's positive work. If it is greater than 90 degrees, the acute angle, obtuse angle, then the work is negative work. Why? Because the component of this force along the displacement would only participate in the work equation, and the perpendicular component will not participate into this. That is why the dot product defines your work. So here, if this alpha is 90 degrees, what do you mean by that? The force acting at point A is at right angle to the displacement shown in this. That is not possible. So you would have, from this definition itself, is dw, du is 0. If alpha is equal to 0, what do you mean by that? This force vector and this is collinear, then your du is going to be F into ds, where this ds is the distance, this magnitude of this dr vector, right? And if alpha is 180 degrees, what do you mean by that? Is force and this collinear, but they act in opposite sense. But the work done is expected to be negative work. It is given by minus F into ds. So this is what you understand from this, right? And then to define what is work of a couple. So before that, what are the forces that participate in that? Is forces applied at a fixed point will not participate. So forces which are not going to participate in the work done calculation, or which do not contribute any work in the system forces, are the forces which are acting at a fixed point in the system, right? Forces applied to a fixed points. Forces applied to a fixed point in the physical system. So what is that point? Frame which is having support, one simply supported frame. One point is hinged, other point is a roller. The hinge point will not have any translation. If I apply an external force at the hinge point, there will be no displacement possible, and that force will not participate in the work equation. So force applied to a fixed point in the physical system will not do any work. Similarly, forces acting at right angle, that's what you have seen here. Forces acting at right angle, perpendicular right angle to the displacement. Displacement will not do work. What is an example? You see there is a block which is translating on a rough surface or expected to impede its motion on a rough surface, will have its reaction at an angle to the vertical. So the angle made by the resultant of horizontal vertical component of the vertical is what is called the friction angle that you have seen. So you will be able to resolve that reaction as a friction force resisting the expected motion and a force perpendicular to the contact surface. The force which is perpendicular to the contact surface will not participate in the equation, whereas force collinear with the contact surface, tangential to the contact surface, acting against the displacement would create participate in work equation, but that work would be a negative work by the friction force, right? And similarly, you have forces which are acting the reaction between a contact surface of smooth contact surface, that would be a triangle to the contact surface, will not participate in the work equation. These are all some of the example of forces which will not participate in the work equation. Now, what is work of a couple? You know, a couple means it's a couple moment, couple moment produced by equal magnitude opposite sense force which are separated, which are parallel, right? That is what is a couple. So the work done by a couple moment would be defined as couple moment times d theta. So here this angular d theta is what is d theta is angular displacement, where here dr is referring the linear displacement, and here it is an angular displacement. Okay. So you would have the couple moment multiplied by d theta would give you what is work of a couple. You know what do you mean by couple, right? You want more elaboration on that? We can have like this. You have a rigid body represented by a line AB, right? And this is now acted upon by a couple. So how do I represent a couple? By equal forces F of same magnitude separated by this distance is what is forming a couple. So this would make my rigid body to move to a new position, say A dash and B dash. So this involves there is some translation as well as rotation. So there is some translation as well as rotation, right? So from here to here it is translated, and this rotation d theta is also there. So the position from here to here changed is what is dr and dr1, let us say, and this is dr2. So if I have this change in position from AB to A dash B dash can be expressed through this. So let us call this distance B to B. So from here A is moved, and then this is B dash, and call this is B double dash, where there is a rotation of this is also accounted because of couple. So this is going to be R dr2, this distance. So R dr2 is this. What do you mean by that? For that, I would have my reference point O, and A is given by RA vector, and B is given by RB vector, and this distance is given by R vector. And that is what is, so this length is R vector, and that is displaced here. R into dr is what is defining, R dr2 is what is defining here. So I can rewrite this equation du as F into dr2. So it is F dr2 is dr2 is dr2 is R into dr2. F into dr2. So this dr2 Sorry, this is not RDR2, this is DR2, right? DR2 is RD. From here to here is DR1 plus DR2. So this is F into DR2, and that would be same as F into R d theta. So F into R is what is the couple here. So that's what is M d theta. That is how we write. So this is work of a couple. So it's simple that when you look at a couple acting on a rigid body, that into angular displacement, which would be considered to be virtual displacement, will produce a virtual work. So while solving that will be easier. This all just to understand the definition I'm explaining you, then we'll get into that. So similarly, work of a force during a finite displacement that you have seen, you also have work of a force by weight and spring, right? So let's understand what do you mean by work of a weight. So the displacement is downward direction due to the weight, then it is positive work. If it is upward, it is negative work. And the work is independent of the path followed. So for example, let us consider an arbitrary path, something like that. I have here a block a rigid body A at a distance from here y1, and that is to reach this uphill here. This is position A2, this is A1, and it reaches to the position 2, that is state A2. And this distance is say from here is y2 height. Now, the weight of this block is so let me have an intermediate location. This block weight is W, and this has to move with a change in distance given by dy. Then I can define, so this height is dy. Then I can define the work of a weight as minus W into dy. Why minus W into dy? Is because weight is acting down, but the block is moving against this moving up. So it's minus W into dy. And you can further rewrite this as an integral of this. So minus W integral y1 to y2 dy. So that's going to be minus W into y going from y1 to y2. So that's going to be W into y1 minus y2. So that's what is work of a weight. So it is change in potential energy, you can say, in this case, where it is mg and y1 is the height at position 1, y2 is the height at position 2. So change in potential energy, and here potential energy with respect to this horizontal reference is lower than that of this reference. So the weight moving from point 1 to 2 would have a negative work there. And simply it is change in potential energy independent of the path followed if the system is conservative, right? So weight only. So weight force would be a change in potential energy. If I have to consider if this surface characteristics and there is a friction force on, then the system is non-conservative system. So the total work done in the system here, if it is conservative, it is only due to this weight that's corresponding to the change in this potential energy. You can say like that. All right. Now, work of a force exerted by a spring. Next. Fourth one. Work of a force exerted by a spring. So how do you define this? So look at that. I have a spring on a horizontal platform and a block attached at the end of the spring. say this is now the position A naught, let us say. Right? So I'm going to give a displacement for this. Because of that, I'm going to have a force that is exerted in the spring or by the spring onto this block. So now let's say this is point A naught position where there is no deformation in the spring. So now what is happening is I'm stretching this spring, means I'm pulling this block to a position say A1 where this displacement is say x1. So the moment if I pull this like this, so this is the horizontal platform. So I can have this block constrained to go on this smooth horizontal surface assume for a time being. So now from the initial position, the displacement in the spring is x1. So if I further stretch this, and that would be the expected final position given by x2. In between these x1 and x2, I can consider the free body diagram here on a smooth surface. The surface is smooth. The weight acts in this direction, and you know the spring force is acting in this direction, which will try to get this block always to the position A0. And you would have, since it is a smooth surface, the normal reaction and friction force. So friction force. The direction of friction force is against the expected motion. So this is friction force. And that friction force, F K, right? So now, if it is smooth surface, this Fk is 0. The smooth surface, so Fk is 0. So this is not there. Only you would have your vertical reaction R. And WR balances and they are at right angle to the expected displacement. So this too will not participate in the work done equation. Just some time back we have seen. So it's work done only by the spring force now, and that force is Fs, and that Fs is defined as a spring constant K called force per unit deformation. That's what is defining spring constant into dx. Into dx. Right. So how do you now get your expression of work done? Is like this. So the work done du would be minus Fs into dx. Minus Fs into dx. Minus Fs into dx. Why minus sign is because the direction of the force is always bring this block to the equilibrium neutral position, whereas the block is displaced from initial position to x1 further to x2. So if our observation is from x1 to x2, there is a deformation already present x1, and from that position x1 to x2 this is displaced, but the free body diagram is intermediate state of your block. So the work done by the force exerted on the spring is minus Fs into dx. So I can substitute this Fs as k into this is not dx, we call this as displacement, finite displacement x, or delta you can say. Here in our case, let's call this as k into displacement x. So displacement x is what at any point of time from here I consider displacement x. So k into x is what is spring force. So if I substitute that here, it is kx dx. That is going from x1 to x2 is what is du. So if I work out this, so I'm going to get k into x squared by 2, that goes from x1 to x2. So I can rewrite as half k x1 square minus half k x2 square. This is what is du. So if x1 is smaller than x2, so obviously this is 0. If x1 is greater than x2, that means work done by the spring. So the position is from here to here, it is moving. So the displacement and the force is in the same direction. Whereas if it is from 1 to 2, then it is against the displacement, the spring force acts, so that would become negative. So in general, you'll write work done by a force exerted by a spring is given by half k x1 squared minus half k x2 squared. Right, so this all you have understood. With this understanding, let us get into a problem that involves a connected body system and try to solve that.